Welcome to this presentation on the empirical validation of magnetic force. In this study, we investigate how a current-carrying wire behaves inside a magnetic field. Our goal is to break down the theoretical equation into measurable variables and verify each one experimentally. The theoretical basis states that a wire carrying an electric current within a magnetic field experiences a force. The magnitude of this force depends on three key variables: the current, the length of the wire within the field, and the magnetic field strength. When the angle between the current and the field is 90 degrees, the force reaches its maximum and the equation simplifies. To determine the direction of the force, we apply the right-hand rule. The current flows along the wire, the magnetic field runs between the poles, and the resulting force is perpendicular to both. By maintaining a 90-degree angle, we ensure the simplest and most direct relationship between the variables. This diagram illustrates the experimental setup. It includes a DC power supply to control the current, a conducting wire placed within a magnetic field generated by magnets, and a balance used to measure the resulting force. This setup allows us to convert magnetic force into measurable data. Our experimental method focuses on isolating variables. First, we vary the current while keeping length and magnetic field constant. Next, we vary the wire length while keeping current and field constant. Finally, we vary the magnetic field strength while holding current and length fixed. In this experiment, we examine the effect of electric current. The wire length is fixed at 42 mm, and the magnetic field is kept constant using 6 magnets. As the current increases, the measured force also increases, indicating a direct relationship. The graph clearly shows a linear relationship between force and current. As the current increases, the force increases proportionally. The strong correlation confirms that force is directly proportional to current. In the second experiment, we investigate the effect of wire length. The current is fixed at 5 amperes, and the magnetic field remains constant. We vary the length of the wire within the field and observe the resulting force. The results show a clear linear relationship between force and wire length. As the length increases, the force increases proportionally. This confirms that force depends directly on the length of the wire within the magnetic field. In the third experiment, we study the effect of magnetic field strength. The current and wire length are held constant, while the number of magnets is varied to change the field strength. As the field increases, the measured force also increases. The graph demonstrates a linear relationship between force and magnetic field strength. Increasing the field leads to a proportional increase in force, confirming the final component of the equation. By combining the results of all three experiments, we observe that force is directly proportional to current, wire length, and magnetic field strength. This leads us to reconstruct the equation: force equals current multiplied by length multiplied by magnetic field strength, when the angle is 90 degrees. In conclusion, the theoretical model has been successfully validated through experimental evidence. The magnetic force acting on a current-carrying wire behaves exactly as predicted, confirming the accuracy of the equation and its representation of physical reality.